It's 11:01, so we can start. Luis?
Yes, well, thank you everybody for coming. It is my great pleasure to introduce you today to our speaker, who is Nafiseh Kiani. She's a PhD student in our program. She is in the Dr. Nani's lab. And I believe she started her PhD around the same time I arrived to UM, 2019. And she has been working, she's a structural engineer. And here at UM, she has been working on how to use FRP on reinforced concrete structures. And I think she's gonna tell us more about that during this her talk. So Nafis, thank you for being the speaker, and the floor is yours.
Thank you. Hello everyone, this is Nafis. I'm a PhD student in civil engineering at the University of Miami, and today I'm gonna talk about the FRP bars for reinforced concrete structures. So the objective and the purpose of this presentation is to get familiar with the FRP bars and mechanical properties of the FRP bars, and get familiar with the behavior of the FRP bars in reinforced concrete structures, and review some design considerations that a civil engineer should know before designing the reinforced concrete members with FRP bars. So first, I'm going through the problem statement that we have for reinforced concrete structures, where should FRP bars be used, and the mechanical properties of the FRP bars. Then I will give you some standards and guides that are available for FRP bars, and the flexural response of the FRP bars and shear responses. In reinforced concrete structures, the corrosion is a very big issue of the steel reinforcement. The corrosion can decrease the service life of the structures. The corrosion can also cause high repair costs. It increases the deflection, increase the cracks, and finally, the structure may fail due to the corrosion effects. But there are different traditional efforts that are using to mitigate the corrosion, like adding admixture to concrete mix, increase the concrete cover, or change it the concrete mix, doing membranes and overlays, or using epoxy-coated galvanized or stainless steel. But unfortunately, sometimes these efforts are not effective in aggressive environment, and we still have corrosion. We still see corrosion in all the, concrete structures. Like you could see in this picture that we have a very, intense corrosion the part of the bridges. So the fact is the infrastructure owners are seeking to increase the service life of the concrete structures up to 100 years and reduce the maintenance costs. But unfortunately, with these available construction materials, they are not reliable to meet all these changes. They need periodic monitoring. The concrete structures needs to be repair, needs periodic monitoring, and the cost is a lot. Like in the US, the total annual cost of the corrosion was reported as $276 billion a year in 2002, based on the infrastructure report. And the bridge deck maintenance due to the corrosion is around $2 billion according to the FHWA reports. It's a big number. So we are thinking that instead of the mitigation, why not eliminating the problem? The solution is that we are using the FRP reinforcement instead of the steel reinforcement in concrete structures. What is FRP? FRP is fiber-reinforced polymer rebars that are known as alternatives to steel reinforcement to eliminate the corrosion in aggressive environments. The FRP bars, as you could see in the picture, they are made of a fiber plus resin. The fibers could be glass, could be carbon, could be aramid or basalt, and the resin could be epoxy or vinyl steel. The most common among different type of the FRP bars, the most commonly FRP bars that are using as a structural reinforcement in concrete structure are GFRP bars or glass FRP bars. So the key benefits of using the FRP bars is that we are using non-corrosive and non-metallic reinforcement, and they have higher tensile strength than the steel. They are lightweight. The weight of the FRP bars are 1/4 of the weight of the steel, which can result in a very saving in a shipping. And they are transparent, and magnetic fields and radar frequency. They are electrically and thermally non-conductive, which is very good for MRI and medical equipment. And they have a very simple installation and ease of application. So the question is that where should FRP be used? The FRP could be used in any concrete structures that are susceptible to corrosion, or some concrete structures that need minimum cover, concrete cover. It could be used in seawalls, in piles, and like these, in piers, in marine structure, in bridge decks, in slabs, and in also parking garage. As you could see in a picture, these are all the concrete members that are using GFRP bars instead of the steel to eliminate the corrosion. So there are different types of the FRP bars: the glass FRP, the carbon FRP, the basalt FRP, and the ceramic. They are very different based on the type of the fibers. They have different strengths and mechanical properties. The types of the resin which is used in the manufacturing procedure of the FRP bars could be thermoset or thermoplastic. The difference is that the FRP bars with thermoset resin cannot be bent after the resin polymerization, because it means that the GFRP bars cannot be bent in the side, but they are available as a pre-manufactured or prefabricated straps or ties. Vinyl ester resin is the most commonly used resin, which are using for producing GFRP bars. Epoxy also is good for basalt FRP bars, but among different resins type, the polyester is no longer allowed because of the poor quality according to the ASTM standard. FRP bars have different coating, different texture, and or different surface deformation. As you could see in a picture, they are available in a sand-coated, improved surface, in a helically wrapped, in a wrapped, or different type of the coating are available for these reinforcement. Also, FRP bars are available in different shapes, like the straight bars as internal reinforcement, as bent bars or stirrups, and like the spirals, or also they are available in twisted strands for pre-stressed concrete uses for pre-tension. The FRP bar sizes are same as the steel bars. They are available up to number 10, and the bar diameter, the nominal cross-sectional area, and everything is available according to the ASTM D7957 standard, which is very specific for the FRP bars. The important material properties that affect the strength of the FRP bars are amount of the fiber that the manufacturers are using during the creating the FRP bars, the type of the fibers, the type of the resin, and the fiber orientation, and the rate of the curing and the service temperature. They are very have an important impacts on the strength and the final ultimate strength of the FRP bars. But another and the most important properties of the FRP bars are is that the FRP bars are anisotropic. It means that their strength in the fiber direction is much higher than the transverse direction, and the FRP bars, so they have higher strength in the fiber direction, but they have a low shear strength. And they are elastic up to failure. They are non-ductile. As you could see in this picture, there are different types of the FRP bars that are compared to stress strain of the steel. And if you see the picture, you will see and compare the black line, which is for the steel, to yellow line, which is for aramid FRP, you could see that the stress strength curve of the FRP is linear elastic up to failure. There isn't any yielding point like this. You will notice that all the FRP bars, like the purple is for carbon, and the green is for glass FRP, and the red one is for basalt FRP. All these three types of the FRP bars have higher tensile strengths than the steel, and also they have low modular elasticity compared to the steel. So based on these mechanical properties, you could conclude that they cannot be used in seismic areas because there is no plastic hinges during the members with FRP bar, and they have higher tensile strength, but they are less stiff than the steel. So these properties provide less confinement to the concrete and RC member, and the low modular plasticity affects the deflection of the RC members that are using the FRP bars. So there are many differences between the FRP and the steel. The advantages is that we are using non-corrosive and we do not have any more corrosion. And we have higher tensile strength, we have a lightweight and reinforcement, and they have high fatigue endurance. And they are electromagnet neutrality. But the disadvantages is that there is no yielding, we do not have any warning before the failure in concrete structures. They have low shear strength, they have low modular elasticity, which affects the deflection of the concrete structures. And they cannot be bent in the field, but the straps and ties are available in like the pre-bent shapes. And they need more and longer development lengths in reinforced concrete structures. And the most challenges that now the engineers are facing is the splicing of the FRP bars. That my PhD research focuses on the splicing of the FRP bars because it's a very challenging in the field. They cannot bend the FRP bars, and the splicing it would be a very important challenge in the field. So there are two types of this splicing method. The first is a lap splicing, so lapping by putting two parallel reinforced bars together. But the lap splicing is not practical in many applications because when the FRP bars needs longer development lengths, assume that we have a very heavily reinforced concrete structure, so it causes congestion at its last location. And also, another method is mechanical splicing, using mechanical devices to connect two reinforcing bars. The mechanical splicing, they are more effective than the lap splicing. They reduce congestion, splice location, and they allow to stage construction for FRP bars. And we do not need to bend or strain the FRP bar. So there are different types of the specification and standards which are available for FRP bars. In the case of the material specification, STMD 7957 is used as a minimum requirement for the material of the reinforcing FRP reinforcement. And also Florida DOT provides a specification to set a minimum requirement that can be used as a material properties for design purposes. In the case of the design of the building and structure, ACI 440 committee provides a guide for the concrete structure that are using the FRP bars is very similar to the ACI 318 for the building that we are using for the designing the concrete members is steel reinforcement. And in the case of the infrastructure and bridges, we have AASHTO LRFD GFRP, which in the last version of the this specification is the second edition. And any civil engineer can use this for designing the bridge and infrastructures. Considering different mechanical properties of the FRP bars, the they have different responses in the case of the design. Like the design tensile strengths of the FRP bars are given based on the ACI, they are reduced compared to the steel by giving an environmental reduction factors, which is very different for different type of the FRP bars, and it depends on the exposure of the reinforcement, the environment, and these equations are based on the ACI 440 committee. That's you can use, and you can go through the guide and see that's what's the difference between different reduction factors for different FRP bars. And also the concrete members with FRP bars, they have different flexure responses, but the assumption and the theory is the same. The assumption of the flexure members is that the plane sections remain plane after deformation, and the ultimate concrete strength is assumed 0.003. The tensile strength of the concrete is ignored, and the FRP is perfectly assumed to be bonded to the concrete. It means that the strain in the reinforcement would be equal to the strain in the concrete. But the difference is that the stress strain of the FRP is linear elastic up to failure, but for the steel, we were assuming the steel was plastic. And the theory is the same. The capacity needs to be greater than the demand, and the moment capacity depends on the different failure mode of the flexure members. The failure mode could be compression control, which is start by the concrete crushing when the reinforcement is greater than the balance reinforcement, and it could be tension control, which start by the FRP rupture when the reinforcement is less than the balanced failure. And the theory and the using the stress strain curve in terms of the computing the tension force and the compression force in the member, or using compatibility strains, are the same. And the theory is the same, but the mechanical properties and some design consideration are different for the FRP bars. And the failure mode could be balanced failure, that it means that the amount of the reinforcement ratio that are used in FRP in members is equal to the balanced failure. And this equation for the balanced failure are available in ACI, and the tension force and also the compression force, they are all given in the ACI 440 committee. In the case of the concrete crushing failure mode, the moment capacity equation is given by the ACI and Ashton as this equation, and also the in this equation, it's the same, just the strength of the FRP is different, and the stress of the FRP is given also in this equation ACI and Ashton. In the case of the, tension control and tension failure, the stress plot in the stress plot is not applicable because the ultimate concrete strain may not be attained, and so to simplify the design, the conservative procedure is proposed, and we are using the balance failure. And the stress reduction factors are different for the FRP bars, based on the depends on the failure mode. That's the failure is based on the FRP rupture, or is the compression control start with the concrete crushing. So also ACI 440 suggested and recommended different reduction factors for FRP bars. So as a conclusion, for the concrete structure that are using the FRP bars instead of the steel bars, the flexure capacity of an FRP member depends on whether the member is controlled by the tension and compression failure. The FRP reinforcement is brittle. And in most cases, the serviceability requirement governs the design, but the allowable stresses under sustained or cyclic loading must be checked. And the flexure behavior is not ductile, and therefore the safety factors are increased. And also the reduced bond properties affect the development plans and crack controls in flexure members. In the case of the shear capacity, the theory is the same. The shear capacity needs to be greater than the demand. And the nominal shear resistance, it would be the contribution of the concrete, which is VC plus, and the shear reinforcement, which is VF. In the case of the contribution of the concrete, it's different between the steel and the FRP. If you consider two similar cross section, the one and the left one is using the FRP and the right one is using the steel. In the equation of the VC for the steel, we are using a D for axial stiffness, and for the FRP we are using KD, which is very less than the steel. It means that the contribution of the concrete is reduced, and also the contribution of the shear reinforcement is reduced for the FRP, because the VF equations depend on the FRP, and it's the tensile strength of the FRP for shear design. So the tensile strength of the FRP for shear design, it depends on the modular elasticity, which I said it's the FRP bars have lower modular elasticity, so it's reduced. And also in the bent portion of the FRP bars for these drops, the ACI 440 committee is suggested that equation for the bent shear strength of the FRP straps, which depends on the internal radius of the bent portion and bar diameter. And as a conclusion, the contribution of the both concrete and FRP straps to the shear strength is both reduced as a result of the reduced axial stiffness of the FRP flexure reinforcement. And the strength of the FRP straps is reduced at the bend location. And for designing, the simple bend shape is like a rectangular are preferred, but they are available in any shapes and any sizes. For designing the members with FRP, the closer spacing is usually required because of the lower strength and stiffness compared to the steel, but the structural theory and the equations remain mostly the same. So at the end, I would like to acknowledge my supervisor, Professor Antonio Nani, for all his supports and all his supports that I received from during my PhD students. Thank you. Any question or comment?